Our galaxy is not traveling through space alone. It is caught in a vast and mysterious current, pulled toward something we cannot see. This is the cosmic mystery of the Great Attractor, a hidden gravitational anomaly of staggering scale. For decades, astronomers have known the Milky Way, along with millions of other galaxies, is moving at an incredible speed toward a specific point in the cosmos. But what is pulling us, and why is its true nature so frustratingly difficult to observe? By the end of our investigation, you will understand the invisible architecture of the universe and our surprising place within it. We will uncover why an entire side of the sky remains obscured, and how dark matter shapes the destiny of everything we know. What does it feel like to realize your entire home is being steered by forces you cannot perceive? The universe's grand expansion should be the only motion that truly matters. After the initial event, space itself began stretching, carrying galaxies away from each other like raisins in a rising loaf of bread. From any vantage point, everything should appear to be receding in a smooth, predictable flow. But when astronomers began measuring with greater precision, they noticed something was off. Galaxies were not just riding the cosmic tide, they were also swimming against it. They possessed their own individual speeds, slight deviations from the uniform expansion known as peculiar velocities. Think of it like leaves floating down a wide, slow river. While the current carries everything along, a leaf might also spin, or drift toward an eddy, or be tugged by a nearby branch. These small, local movements are the peculiar velocities caused by the gravitational pull of neighboring masses. In the 1970s, scientists started mapping these subtle galactic drifts with new tools. They focused on our immediate neighborhood, a cluster of galaxies called the Local Group, which includes the Milky Way and Andromeda. They calculated how fast we should be moving based on the expansion alone, and then they measured our actual motion. The numbers did not match. Our entire local group was rushing through space far faster than anyone had predicted. It was as if, while floating calmly down that river, our entire raft suddenly lurched sideways, pulled by a current no one could see. This was the first solid clue. Something immense, something with gravity powerful enough to override the background expansion of the universe, was tugging at us from the darkness. The hunt for the source of that inexplicable pull had officially begun. The data painted a startling picture. Our galaxy was not drifting aimlessly, it was racing. Precise measurements revealed the Milky Way, along with our entire galactic neighborhood, is moving at a staggering 600 kilometers every single second. To put that in human terms, that is over 1.3 million miles per hour. We are caught in a flow of matter so vast, so powerful, it defies everyday comprehension. This is not just our galaxy's motion. Every major structure for hundreds of millions of light years around us shares this same relentless trajectory. Picture thousands of individual islands, not scattered randomly in an ocean, but all caught in the same titanic current, all sliding toward the same distant horizon. This coherent rush of countless galaxies became known as the bulk flow, a river of stars and dark matter on a scale that humbles the imagination. Astronomers traced the vectors of this motion across the sky, and they all converged. They pointed like cosmic compass needles toward a single region of space, a gravitational epicenter hidden behind the thick stars of our own Milky Way's central bulge. This mysterious destination, the source of the pull, needed a name. They called it the Great Attractor. The label was perfect. It was grand, it was ominous, and it admitted a profound ignorance. We knew something was there, exerting a force that commands the motion of superclusters, but we could not see it. The very heart of the mystery was veiled by the crowded core of our own home galaxy, placing it in what astronomers call the Zone of Avoidance. The search was now defined by a paradox. The most significant gravitational landmark in our local universe was also the most hidden. The compass of cosmic motion pointed toward a very specific address in the sky. All those converging galactic paths led astronomers to a spot in the southern hemisphere, in the general direction of the constellations Centaurus and Hydra. This was the calculated focal point, the gravitational sinkhole towards which our entire local universe was sliding. But pinpointing its location only deepened the mystery, because this address came with a major observational problem. The Great Attractor does not lie in some clear, dark void. It sits almost perfectly along the crowded central plane of our own Milky Way galaxy. Think of trying to see a distant city skyline, but your view is completely blocked by a nearby, brilliantly lit mountain range. That is the challenge astronomers faced. The disk of our galaxy is filled with immense clouds of interstellar dust, countless stars, and glowing nebulae. This creates a dense, luminous band that wraps around our entire sky. For anyone trying to peer through it to the universe beyond, this band is a fundamental obstacle. Astronomers even have a name for it, the Zone of Avoidance. It is not that there is nothing to see out there. It is that our own galactic neighborhood is literally in the way, obscuring perhaps a quarter of the extragalactic universe from our clear view. So the most significant gravitational landmark we had ever detected, the force steering millions of galaxies, was hidden in the cosmic equivalent of a permanent fog bank. Optical telescopes which rely on visible light were nearly useless. The dust scatters and absorbs that light, rendering anything behind it a faint, blurry smudge. The Great Attractor was a shout in the dark, but we were trying to hear it from inside a soundproof room. To solve this, science needed a new way of listening. To see through the galactic fog, astronomers had to change the very type of light they were looking for. They turned their instruments away from the visible spectrum toward wavelengths that could slip through the dust unseen. Radio waves with their long, penetrating energy became the first key. Giant radio telescopes began mapping the sky, listening for the faint whispers of hydrogen gas, the fundamental building block of galaxies. These surveys did not see starlight. They detected the signature glow of cold hydrogen clouds that trace the spiral arms of galaxies hidden behind the Milky Way's bulge. The initial maps were revelatory. Where optical telescopes saw only a blank, starry wall, the radio data revealed a crowded sky. Dozens, then hundreds of galaxy signatures emerged from the noise. The Zone of Avoidance was not a void at all. It was a treasure trove of unseen structures, a hidden continent of stars suddenly coming into view. Soon, infrared observatories joined the effort. Infrared light, with wavelengths longer than visible red, is less easily scattered by fine dust grains. Space-based infrared telescopes, peering from above Earth's atmosphere, began to paint their own picture. They detected the gentle heat glow of billions of old stars, the collective warmth of entire galaxies lurking behind the obscuration. The combined data from these new eyes was undeniable. The direction of the Great Attractor was not empty. It was teeming with mass. The original idea of a single, monstrous object pulling us in began to shift. The sheer number of galaxies found in that region suggested something far grander. The Great Attractor was not a lone giant, but likely the gravitational heart of an unimaginably large congregation of galaxies, a supercluster whose core of mass lay directly in that obscured zone. The pull we felt was the collective gravity of thousands of galaxies, all bound together in a single, titanic knot of dark matter and stars. We were not being reeled in by a cosmic angler. We were being swept along in the current of the largest river system in our local universe. This emerging picture forced a complete redefinition of the Great Attractor itself. It was not a singular object in the traditional sense, not a supermassive black hole or a lone, monstrous galaxy. Instead, it was a place, a gravitational address, Scientists came to understand it as the central core, the downtown, of the largest cosmic structure we have ever called home. This structure has a name, the Laniakea Supercluster. Laniakea is a Hawaiian word meaning immeasurable heaven, and it is a fitting title for a congregation of over 100,000 galaxies, spanning more than 500 million light-years. Within this vast web, every galaxy, every cluster, flows along invisible filaments of dark matter toward the same gravitational basin. The Great Attractor is simply the deepest point in that basin, the bottom of the valley toward which all the rivers of stars are flowing. Our own Milky Way galaxy resides far out on one of Laniakea's sprawling suburban filaments. We are not at the center of anything. We are participants in a motion far greater than ourselves, residents on the remote outskirts of an immeasurable heaven. And this redefinition solves one mystery only to introduce a grander one, for Laniakea itself is not stationary. Our entire supercluster, with the Great Attractor at its heart, is also in motion. It is being pulled, in turn, by something even larger. The hierarchy of influence stretches onward, a cosmic cascade of gravity where every structure is both an attractor and the attracted. The question shifts from what is pulling the Milky Way to what is pulling everything. Deep within that obscured zone, at the very coordinates of the gravitational pull, lies a colossal knot of galaxies. This is the Norma Cluster, a dense swarm of ancient stars and dark matter some 220 million light-years from Earth. To our instruments, it appears as the brightest, most massive concentration of visible matter at the heart of the Great Attractor. Thousands of galaxies are bound together here in a relatively small volume of space, their collective gravity creating a profound well in the fabric of the cosmos. It is a spectacular and fitting candidate for the source of the pull, like finding a mountain at the end of a river. Yet when scientists did the math, a discrepancy emerged. They calculated the total mass of all the galaxies they could see in the Norma Cluster, even estimating the vast halos of dark matter that must surround them. The sum was immense, beyond human comprehension, but it was still not enough. The gravitational force required to explain the 600 km/s motion of our Milky Way and the bulk flow of our entire local universe was greater still. The Norma Cluster is a giant, but it is not the only giant in the room. Its tremendous mass is a major contributor, a central landmark in this hidden territory, but it cannot be acting alone. So what else is there, lurking in the darkness alongside it, adding its invisible weight to the scale? The search had to widen again, looking not for a single source, but for an entire hidden geography of mass. The numbers simply do not add up. When astronomers meticulously calculated the total mass of everything they could see at the Great Attractor's core, including the immense Norma Cluster and all the surrounding galaxies, they arrived at a staggering figure. It is a weight equivalent to many thousands of Milky Ways. Yet when they performed a separate calculation, one based on the raw gravitational force needed to accelerate our entire supercluster at 600 km/s, the required mass was far, far greater. This is the mass budget shortfall, a fundamental cosmic accounting error. The visible universe, for all its splendor, is bankrupt. The stars, the gas, the glowing clusters we can detect with our finest instruments, they account for perhaps only a tenth of the gravitational pull we actually feel. It is as if you are trying to understand why a massive ship is listing to one side. You can see all the cargo on the deck, the containers, the machinery. But no matter how you stack and count it, the visible load is not heavy enough to explain the tilt. There must be something else, a hidden ballast deep in the hold, invisible from where you stand, that provides the missing weight. In the cosmos, that hidden ballast is dark matter. This discrepancy is not a failure of our math. It is one of the most profound confirmations in modern astrophysics. The Great Attractor's true power does not come primarily from the galaxies we have painstakingly mapped. Its overwhelming gravity is the product of an immense, unseen ocean of dark matter in which those galaxies are merely floating islands. The structure pulling us is by mass mostly made of something we cannot see, touch, or yet fully understand. It is a ghostly skeleton, and the universe we perceive is just its luminous flesh. This missing mass is not an error in our observations. It is the signature of the universe's true architect. The dominant form of matter in the cosmos does not shine, glow, or reflect a single photon of light. We call it dark matter, and it is the invisible engine shaping everything we see. Think of it this way: if the entire cosmic structure were a magnificent city, the stars and galaxies would be the glittering lights in the windows. But dark matter would be the steel framework, the concrete foundations, and the hidden wiring holding the entire metropolis together. We cannot see that framework directly, but we know it must be there because without it, the city would collapse. The buildings, the lights, they simply do not have enough mass on their own to explain the stability and the motion of the whole. Dark matter interacts with the universe through one fundamental force, gravity. It does not emit light, it does not absorb light, and for the most part, it seems to pass right through ordinary matter without a whisper. We only know it exists because of its overwhelming gravitational influence, like feeling the steady pull of a powerful magnet hidden beneath a cloth. The Great Attractor provides one of the most dramatic and large-scale pieces of evidence for this hidden architecture. The gravitational anomaly that first puzzled astronomers is not caused by the visible galaxies alone. It is the combined pull of those glittering islands and the immense, unseen ocean of dark matter in which they are all embedded. Every galaxy cluster, including the Norma Cluster at the heart of the attractor, is believed to be seated within a vast, diffuse halo of this mysterious substance. These halos are titanic, often extending far beyond the visible edges of the galaxies themselves, and they contain many times more mass than all the stars and gas within. So when we feel the pull toward that point in the sky, we are not just being reeled in by the galaxies we have mapped. We are responding to the deep gravitational well carved out by an entire hidden continent of dark matter, a continent whose brightest cities are the clusters we can finally see through the dust. This realization transforms the Great Attractor from a mysterious destination into a profound lesson. It teaches us that the cosmos is built from a substance we are only beginning to fathom, and that the most powerful forces guiding our journey are the ones we cannot see. Just when the story seemed to settle, the cosmos revealed another layer. The gravitational mystery did not end at the Great Attractor. In the 1980s and 90s, as our maps of the large-scale universe grew more detailed, astronomers made a startling discovery. They found evidence of an even more massive concentration of matter, a gravitational titan located far beyond the Norma Cluster and the heart of Laniakea. This structure lies some 650 million light-years away, in the direction of the constellation Centaurus. It is known as the Shapley Supercluster, named for the American astronomer Harlow Shapley, and it represents the single largest gathering of matter we have identified in our observable neighborhood. To grasp its scale, picture the Great Attractor as a major city, a powerful gravitational center in its own right. The Shapley Supercluster would be the entire continent upon which that city sits. It is not merely a cluster of galaxies, but a dense knot where several immense filaments of the cosmic web intersect, containing dozens of massive galaxy clusters and hundreds of thousands of individual galaxies. Its total mass is almost incomprehensible. This discovery complicated our cosmic narrative in a profound way. The Great Attractor, with all its hidden might, is not the final word. It appears to be in motion itself. The current thinking suggests that the immense gravity of the Shapley Supercluster is pulling on the entire Laniakea Supercluster, including its core. So the Great Attractor is not just pulling us, it is also being pulled. We are caught in a cosmic chain of influence, a gravitational hierarchy where our local flow is merely a tributary to a far greater river. Our Milky Way's journey, then, is a multi-stage voyage. We are moving toward the Great Attractor, which is itself moving toward Shapley. This reshapes the entire quest from a search for a single destination into an understanding of an endless current, a reminder that in an expanding universe, even the mightiest structures are not still. They are all participants in a grand, slow dance orchestrated by gravity across billions of light years. Our galaxy's journey is not a simple fall toward a single point. It is the outcome of a silent, billion-year-long tug of war. Picture two immense teams of cosmic giants, each gripping a rope with our local universe caught somewhere in the middle. On one side, we feel the powerful pull from the Great Attractor, that deep gravitational basin at the heart of our Laniakea supercluster. Its influence comes not just from the galaxies we see there, but from the vast, hidden reservoir of dark matter that gives the entire structure its true weight. This force has been steadily drawing us inward for eons, but pulling from the opposite direction is an even greater force, the overwhelming gravity of the Shapley Supercluster. This distant titan, hundreds of millions of light years beyond the Great Attractor, exerts its own profound influence on everything in our neighborhood. The 600 km/s motion we measure for the Milky Way is not our speed toward just one of these giants. It is our net velocity, the final result after these two colossal gravitational fields have been subtracted from one another. We are moving in the direction of the stronger pull, but our speed is tempered, moderated by the counterweight pulling from behind. This model transforms a simple mystery into a dynamic balance. It explains why we are not hurtling even faster toward the Great Attractor. The Shapley Supercluster acts as a kind of cosmic anchor, its immense gravity applying a subtle but constant brake on our motion. Our observed path through the void is therefore a compromise, a trajectory carved by competing attractions across unimaginable distances. This understanding shifts our perspective once more. We are not merely passengers on a train heading to a single destination. We are more like a boat on a wide river where the current is shaped by the combined pull of the moon and the distant ocean. Our motion tells the story of a relationship between structures, a story written in gravity and dark matter, where every movement is a testament to the unseen architecture of everything. This cosmic tug of war required a whole new map. For centuries, we defined our place in the universe by what we could see, by the bright islands of galaxies scattered around us. But true cosmic geography is not written in light, it is written in motion. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii performed a radical act of cartography. They did not just look at where galaxies are, they meticulously tracked how they move. Using the observed velocities of over 8,000 galaxies, they traced the subtle flows caused by gravity, much like following the paths of leaves on a river to map the currents beneath. The resulting portrait redefined our home. They revealed that our Milky Way is just one member of a vast continent-like structure they named Laniakea, the immeasurable heaven. This supercluster is not a random collection, but a distinct gravitational entity. Its boundaries are not defined by empty space, but by the watersheds of cosmic flow. Picture a vast mountain range seen from above, with rain falling on its slopes. Every drop follows gravity's pull, some flowing into one great river system, others into a neighboring one. The ridgeline between those systems is the watershed. Laniakea operates on the same principle, but on a scale of 500 million light-years. Within its borders, every galaxy, every star cluster, flows along invisible gravitational currents toward the same deep basin. That basin, the lowest point in this immeasurable heaven, is the Great Attractor. It is the gravitational sink toward which all the rivers of stars within Laniakea ultimately drain. This mapping placed the attractor in its proper context at last. It is not a bizarre anomaly or a lone monster. It is the functional heart, the downtown of our local universe. Our cosmic address was no longer just the Milky Way local group Virgo Supercluster. It became a clear and humbling sequence, Milky Way, on the outskirts of the Laniakea Supercluster, flowing forever toward its hidden gravitational core. Mapping an invisible continent required a new kind of vision. The breakthrough came not from a single telescope, but from a coordinated, decades-long campaign of cosmic cartography, a revolution in how we collect light from the depths of space. To peer through the Milky Way's obscuring veil, astronomers launched ambitious, all-sky surveys designed to see in the dark. They built instruments sensitive to wavelengths of light that dust cannot stop. The 2-micron all-sky survey, known as 2MASS, was a pioneer. It scanned the entire heavens in infrared light, the gentle heat glow emitted by stars. This allowed it to see directly through the dusty disk of our galaxy, revealing the faint, red signatures of millions of stars and distant galaxies that had been completely hidden from optical view. It was like switching from a flashlight to a thermal camera in a dense fog, suddenly seeing the warm shapes of structures you knew were there but could never clearly make out. Around the same time, radio astronomers undertook their own monumental effort. The HIPASS All-Sky Survey, or HIPASS, used a giant radio telescope in Australia to listen for a very specific signal, the faint radio whisper emitted by neutral hydrogen atoms. Since hydrogen is the fundamental fuel of galaxies, mapping its radio glow was a direct way to trace galactic structure, even for galaxies whose starlight was completely blocked. These surveys did not produce pretty pictures of spiral arms in vibrant color. Instead, they generated vast, point-by-point catalogs, immense databases of coordinates and velocities. Each entry was a single galaxy, its position and its redshift measured with precision. Redshift, the stretching of light toward the red end of the spectrum caused by the expansion of the universe, provided the crucial third dimension, allowing astronomers to calculate not just where a galaxy is on the sky, but how far away it is. This three-dimensional mapping was the key. It transformed the sky from a flat tapestry of stars into a deep, sculpted landscape of structure. The most ambitious of these projects, the Sloan Digital Sky Survey, began creating a map so detailed it would eventually catalog hundreds of millions of celestial objects. By combining the infrared views from 2MASS with the radio data from HIPASS and the optical depth of Sloan, scientists could finally weigh the hidden regions. They could calculate the total mass present in the zone of avoidance by adding up the gravitational influence of every galaxy found there, both the bright and the faint. This was not a matter of taking a photograph, it was an act of forensic accounting on a cosmic scale. The instrumental revolution gave us the data to feel the shape of the darkness, to trace with scientific certainty the currents of a river we could not see, confirming that the pull we feel is the collective gravity of a hidden world now brought reluctantly into view. The hidden continent of mass revealed by radio and infrared surveys still presented a fundamental problem. We could map the galaxies, but how do you weigh something you cannot see? The answer came from looking not at the stars, but at the space between them, using a form of light our eyes were never meant to see. The universe holds its hottest secrets in the X-ray spectrum. When we point an ordinary optical telescope at a massive galaxy cluster like the Norma Cluster at the heart of the Great Attractor, we see a spectacular collection of individual galaxies, each a swirling island of billions of stars. But this view captures only a fraction of the story. Filling the immense spaces between those galaxies is a superheated ocean of thin gas, known as the intracluster medium. This gas is not cold and dark, it is a roiling plasma, heated to temperatures of tens of millions of degrees by the violent gravitational forces at play as galaxies swarm together. Matter this hot does not glow in visible light, it screams in X-rays. For astronomers, this became a crucial clue. The distribution and temperature of this searing intracluster gas acts as a perfect tracer for the cluster's total gravitational field. Think of it like watching smoke in a completely still room. The smoke does not just drift randomly, it is shaped by the invisible currents of air, revealing the room's hidden airflow. In the same way, the hot X-ray gas is trapped and shaped by the cluster's gravity. It fills the entire gravitational well, mapping its contours with exquisite precision. To observe this, scientists needed eyes above Earth's atmosphere, which blocks X-rays from reaching the ground. This led to space-based observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton telescope. These satellites are essentially giant, orbiting X-ray cameras. When they turned their gaze toward the obscured region of the Great Attractor, they did not see points of light from stars. Instead, they saw vast, diffuse clouds of intense X-ray emission, glowing halos of million-degree gas that enveloped entire clusters of galaxies. The image of the Norma Cluster from Chandra is breathtaking. It shows a brilliant, almost cloud-like sphere of X-rays, far larger than the combined visible light from all its member galaxies. By analyzing this glow, scientists could perform a cosmic autopsy. They could measure the gas's temperature, its density, and how it is distributed. Using the laws of physics, they could then work backwards to calculate the total mass required to hold such a hot, energetic cloud in place and keep it from simply flying apart. The result consistently confirmed what the motion of galaxies had already hinted. The visible galaxies and the hot gas together accounted for only a small percentage of the needed mass. The overwhelming majority, the true source of the gravitational grip, was the invisible dark matter halo. X-ray astronomy provided the final, compelling piece of evidence. It allowed us to literally weigh the Great Attractor's core by measuring the heat of its atmosphere, proving that the mightiest structures in our universe are built upon foundations we can only infer from their shadow. This hidden gravitational architecture leaves a signature in the very oldest light we can see. To understand our place in the cosmic flow, we must look back to the dawn of time itself, to the afterglow of the universe's birth. This is the cosmic microwave background, a faint whisper of radiation that fills every corner of space, a snapshot of the infant cosmos when it was just 380,000 years old. In a perfectly still universe, this ancient light would appear perfectly uniform, a smooth sea of microwaves arriving from all directions with exactly the same temperature. But our universe is not still. We are moving, and our motion through space imprints itself upon this primordial signal in a profound way. Just as the pitch of a siren sounds higher as an ambulance races toward you and lower as it speeds away, light waves are compressed or stretched by motion. This is the Doppler effect. As our entire galaxy, pulled by the Great Attractor and anchored by Shapley, hurtles through space, we are effectively running into the cosmic microwave background radiation coming from one direction and racing away from the radiation coming from the opposite direction. The light we run into gets squeezed, its wavelength shortened, making it appear slightly hotter and more energetic. The light we flee from gets stretched, its wavelength lengthened, making it appear slightly colder. The result is a distinct pattern in the sky, a cosmic lopsidedness known as the CMB dipole. One half of the universe's oldest light appears a tiny fraction of a degree warmer, the other half a tiny fraction of a degree cooler. This hot spot and cold spot are not features of the early universe, they are a mirror reflecting our own journey. By measuring the precise size and orientation of this dipole, scientists can calculate our exact speed and direction relative to this universal frame of reference. The velocity they measure, over 600 kilometers per second, aligns almost perfectly with our motion toward the Great Attractor. This creates a powerful link between the local and the cosmic. The tug of war between Laniakea and Shapley, the gravitational dance happening across hundreds of millions of light years, is not just a local story. It is written into the most universal canvas we have, the afterglow of creation itself. Our rush toward that hidden gravitational basin is so significant, it warps our view of the universe's first light. Even light cannot travel through the cosmos in a straight line. The presence of mass warps the very fabric of space-time, creating curves that alter the path of anything passing through, including beams of light from the most distant galaxies. This phenomenon, predicted by Einstein over a century ago, is called gravitational lensing, and it has become one of our most powerful tools for weighing the invisible. It allows us to see the shadow of mass itself. Around the region of the Great Attractor, this cosmic trick of the light provides a final, independent line of evidence, a way to measure the hidden structure directly without relying on the motion of galaxies or the heat of X-ray gas. The effect comes in two primary forms, each telling a different part of the story. Strong gravitational lensing creates the most dramatic cosmic mirages. When a truly immense concentration of mass, like the core of a massive galaxy cluster, sits directly between us and a far more distant galaxy, the distortion can be spectacular. The background galaxy's light is bent and smeared into bright arcs, rings, or even multiple copies of itself, arranged around the foreground cluster like a ghostly halo. It is a perfect Einstein ring, a signature of profound warping. While the dense core of the Norma Cluster can produce such effects, the broader Great Attractor region is more often mapped through its subtler cousin, weak gravitational lensing. Weak lensing is a far more widespread but delicate fingerprint. Instead of creating obvious rings or arcs, the combined gravity of all the dark matter and galaxies in a vast region like the Great Attractor ever so slightly distorts the shapes of millions of faint background galaxies. Imagine looking at a distant streetlight through the rippling heat waves rising from a hot asphalt road. The light shimmers and its shape appears subtly stretched and warped. Weak lensing works on a similar principle, but the distorting medium is not heat. It is the gravitational field of all the unseen mass between us and those distant galaxies. Each individual background galaxy's distortion is infinitesimally small, far too slight to notice by eye. But by using powerful telescopes and sophisticated software to analyze the shapes of hundreds of thousands, even millions, of these distant galaxies across a wide patch of sky, astronomers can detect a consistent pattern. They can see a statistical shearing, a gentle stretching of galaxy shapes that points toward the centers of mass. This vast survey work creates a map not of light but of gravitational influence. When these weak lensing surveys are focused on the obscured zone toward the constellations Centaurus and Hydra, the map they produce is unmistakable. It shows a profound gravitational well, a broad region where the shapes of background galaxies are systematically stretched in a way that points toward the Great Attractor's core. The pattern confirms the presence of an immense amount of mass concentrated in that direction, and its scale aligns perfectly with the measurements from galaxy motions and X-ray halos. More importantly, the lensing map traces the distribution of all the mass, both visible and dark. It reveals the shape and extent of the dark matter halo that cradles the Norma Cluster and its neighboring galaxies. The lensing data shows this halo is not a neat sphere. It is an elongated structure stretched along the filaments of the cosmic web, confirming that the Great Attractor is indeed the central node of a much larger flow of matter. This technique provides a direct geometric measurement. We are no longer inferring mass from motion or heat. We are literally charting the curvature of space itself. The bent paths of ancient light beams serve as silent witnesses, drawing for us the outline of the unseen continent that guides our journey. The ultimate test of our cosmic understanding lies not in a telescope, but in a machine. We have mapped the flows and weighed the shadows, but can we recreate the universe itself? To answer this, cosmologists turn to the most powerful supercomputers on Earth, building digital universes from the ground up. These are not simple animations, they are rigorous physics experiments conducted inside vast arrays of processors. The goal is breathtakingly ambitious: to start with a nearly uniform soup of matter and energy in the early universe, apply the known laws of gravity and expansion, and simply press play. The most famous of these endeavors is the Millennium Simulation, a landmark project that used over 10 billion simulated particles to represent dark matter, tracing their evolution across more than 2 billion light-years of virtual space and over 13 billion years of cosmic time. The simulation begins with conditions just after the Big Bang, seeded with the tiny, random fluctuations we observe in the cosmic microwave background. Then the clock starts ticking. Gravity begins its relentless work. Over eons of simulated time, the subtle overdensities, the places where there is just a fraction more dark matter, begin to pull in more material from their surroundings. They grow, they merge, they stretch and connect. What emerges from this digital primordial soup is not a random scatter of points, but an intricate, evolving web. Vast filaments of dark matter form, intersecting at dense nodes where galaxy clusters will eventually coalesce. Enormous voids, regions of startling emptiness, open up between these luminous threads. The simulation naturally produces the entire cosmic hierarchy, from the first small halos to the great walls and superclusters we see in our surveys. And when scientists analyze the motion within this digital cosmos, they find the same phenomenon we observe in our own, coherent rivers of virtual galaxies streaming along the filaments toward the deepest gravitational basins. These simulated flows look uncannily like our observed bulk flow toward the Great Attractor. The virtual universe creates its own attractors, not because they were programmed in, but because the physics of gravity and dark matter demand their formation. This is a profound validation. The fact that our best models, when given the correct starting conditions and the known rules, spontaneously generate a universe that looks and moves like our own, is a powerful sign we are on the right track. It tells us the Great Attractor is not a bizarre exception, but an expected feature in a cosmos built upon dark matter and shaped by dark energy. The simulation becomes a time machine, allowing us to rewind our local flow and see how the gravitational landscape that now pulls us first took shape. It suggests that long before the first stars ignited in the Norma Cluster, the destiny of our galactic journey was being written in the invisible geometry of the dark web. Our story is not a special case in a quiet universe. The Great Attractor is not a cosmic oddity, it is the rule. What we are experiencing, this immense and steady pull toward a hidden basin of gravity, is simply the local expression of a universal process. Every galaxy in every corner of the cosmos is likely riding similar currents, flowing along the invisible contours of the dark matter web toward its own regional attractor. We are not being singled out by the universe for a unique journey. We are participating in the standard traffic pattern of creation. Think of the large-scale structure not as a static sculpture, but as a dynamic, slow-motion watershed. Across an entire continent, every raindrop follows gravity's pull, some joining small streams that feed into larger rivers, all eventually flowing toward a few major basins, like the Mississippi or the Amazon. The cosmic web operates on precisely this principle, but across scales of hundreds of millions of light-years. The filaments of galaxies are the rivers, and the dense superclusters where those filaments intersect are the gravitational basins, the attractors. Our Laniakea supercluster, with the Great Attractor at its heart, is simply our local basin. A galaxy in a different supercluster, like the distant Perseus-Pisces chain, would feel its own primary pull toward a different deep point in space, its own version of a Great Attractor. This realization is both humbling and illuminating. It means the mystery we have been unraveling is not about one strange object. it is about the fundamental architecture of reality. The force steering our galaxy is the same force that organizes all structure in the universe, from the smallest groups of galaxies to the largest walls. We are not exploring a bizarre exception, we are finally understanding the norm. Our unique advantage is simply perspective. We happen to live inside this particular flow, so we can measure its details with an intimacy impossible for any other. The 600 km/s motion of the Milky Way is our front row seat to the grand hydraulic system of the cosmos, a system where gravity is the water, dark matter is the landscape, and every galaxy is carried along by the current. Yet gravity is not the only sculptor at work in the cosmos. For all its power to pull galaxies together into magnificent clusters and superclusters, an even more mysterious force is acting on the grandest stage of all. This force does not attract, it repels. It is the enigmatic influence we call dark energy, and its effect is to push the very fabric of space itself apart. While the Great Attractor represents a local victory for gravity, a place where matter has successfully gathered against the tide, dark energy is the ocean tide itself, a pressure inherent to empty space that is slowly but surely overwhelming every structure it touches. This sets up a fundamental cosmic conflict, a tug of war playing out across time. On local scales within superclusters like our Laniakea, gravity reigns supreme. Its pull creates the flows and the basins, the rivers of galaxies moving toward shared destinations. But on the very largest scales, beyond the reach of these local gatherings, dark energy dominates. It is causing the expansion of the universe not just to continue, but to accelerate. Think of it like this: you are building a magnificent sandcastle on a beach. Your hands shaping and piling the sand represent gravity. You can create towers and walls, complex and beautiful structures by pulling grains together. But all the while the tide is coming in. The rising water, representing dark energy, slowly soaks the sand, weakening the bonds between grains. Eventually, no matter how grand your castle, the tide will claim it, dissolving the structure back into the vast, flat expanse. In our universe, the sandcastles are the great walls and superclusters, and the tide is dark energy. For now, within our local neighborhood, gravity's architecture is stable. Our journey toward the Great Attractor will continue for tens of billions of years, with our local group of galaxies eventually merging into the larger Norma Cluster in the distant future. But on a timeline so vast it dwarfs human comprehension, dark energy's influence will grow. As space itself continues to stretch at an ever-increasing rate, the distances between superclusters will become so immense that their gravitational bonds will be severed. The cosmic web, the magnificent filamentary structure that gives the universe its rich texture, will begin to fray. The rivers of galaxies will slow, then stop, as the space between them expands faster than gravity can pull them together. In a future so far away that all stars in our galaxy will have long since burned out, any remaining civilizations would look up to a profoundly empty sky. Neighboring superclusters would have vanished over the horizon of observable space, their light stretched beyond detection. The Great Attractor and all structures like it would become isolated islands in a vast, dark, and ever-growing sea. This understanding frames our present moment as a privileged one. We live in an era where the universe is still richly structured, where gravity's handiwork is visible and dynamic. We can map the flows and trace the filaments. We can feel the pull of a hidden mass and understand our place within a grand local story. That story, however, has an ultimate conclusion written not by gravity, but by the silent, repulsive energy of the void. Our cosmic journey toward a hidden center is but a temporary eddy in a much larger and ultimately dispersing current. The map of our cosmic neighborhood, for all its detail, is still unfinished. Vast stretches remain uncharted, and the true texture of the dark matter web is only roughly sketched. This is not the end of the story. but a call for a new generation of explorers. The next decade will see an unprecedented leap in our ability to see the unseen, driven by two monumental projects that will transform fuzzy shadows into sharp relief. The first is a space-based observatory named Euclid, launched by the European Space Agency. Euclid is not a traditional telescope focused on pretty pictures of nebulae. It is a precision instrument designed for a single, profound purpose: to conduct a cosmic census of dark energy and dark matter by observing billions of galaxies across 1/3 of the sky. Its primary tool is weak gravitational lensing, that subtle stretching of galaxy shapes, but Euclid will perform this measurement with a clarity and scale never before possible. It will detect the faint distortions in the shapes of over 1 billion galaxies, tracing the distribution of the invisible mass that bends their light with statistical power 100 times greater than any previous survey. This will allow scientists to create a three-dimensional mass map of the universe, a tomographic scan of the dark matter skeleton. For the Great Attractor region, this means we will no longer see just a broad gravitational well. Euclid's data could reveal the intricate substructure within that well, the finer filaments and clumps of dark matter that channel the flow of galaxies, painting a dynamic portrait of the attractor's hidden anatomy. Back on Earth, an equally ambitious project is preparing to scan the heavens. The Vera Rubin Observatory in Chile, with its immense mirror and giant digital camera, will soon begin the legacy survey of space and time. Over 10 years, it will image the entire southern sky every few nights, creating the largest astronomical movie ever made. The LSST will detect tens of billions of galaxies and track millions of transient events, but its power for our story lies in its sheer depth and precision. By measuring the positions and shapes of countless galaxies with exquisite accuracy, it will complement Euclid's lensing map with an independent, ultra-detailed chart of visible matter. Combining these two datasets will be like having a perfect map of all the cities, towns, and roads, overlaid with a seismic survey showing the underlying rock formations and fault lines. The synergy between Euclid's deep space lensing and Rubin's relentless optical survey will allow astronomers to weigh the Great Attractor and its surroundings with unprecedented fidelity. They will test whether our current model of the tug of war between Laniakea and the Shapley Supercluster holds up, or if new, unexpected structures are revealed within the cosmic flow. These missions represent a shift from discovery to precision. We know the hidden continent is there. Now we are sending out surveyors to map its every valley, river, and mountain range in the dark. The final chapters of the Attractor's story have not yet been written, because the instruments to read them are only now opening their eyes to the sky. This knowledge carries a quiet, philosophical weight. Our journey is not random. From the grandest spiral arm of the Milky Way to the smallest pebble on a distant world, every single particle within our galaxy is part of this immense directed flow. We are not wanderers in the dark, we are participants in a choreography set billions of years ago. Our cosmic destiny for this epoch of the universe is to follow the curvature of space toward a hidden basin we cannot see. This path was not chosen, it was inherited, written into the distribution of dark matter before our sun even ignited. It forces a profound shift in perspective. We often think of ourselves as the center of our own story, agents of free will and independent motion. Yet on the grandest scale, that agency exists within a current far greater than ourselves. Our entire island universe is being steered. This realization is not meant to diminish our significance, but to redefine it within a breathtaking context. Our quest for meaning, our drive to explore and understand, is itself a product of this cosmic journey. The atoms that form our bodies were forged in stars that formed because gravity pulled gas together along these same dark matter filaments. We are not just passengers on this flow, we are its conscious expression. We are the universe in one small corner, awakening to the fact that it is moving. To understand the Great Attractor is to feel a deep, humbling connection. It ties our fate to the architecture of everything. The same invisible threads that guide galaxies also set the stage for planets to form and life to arise. Our local story of existence is woven into the largest story of structure. We are following a map drawn in darkness, and in tracing its lines, we find our place not at the center, but within a magnificent and ongoing narrative of gravity, matter, and motion. Even with our most advanced maps, the true shape of the darkness remains elusive. We know the Great Attractor is there, a continent of unseen mass, but its finer geography is still a mystery. What is the precise three-dimensional distribution of the dark matter within that vast gravitational basin? Our current models suggest a vast, elongated halo, but is it smooth, or are there dense knots and subfilaments woven through it like currents within a deep ocean? Pinpointing this invisible architecture is crucial because it would tell us exactly how the flow of galaxies is channeled, how the cosmic rivers merge on their way to the basin. Each new, more sensitive gravitational lensing survey, like those from the Euclid mission, brings us closer to answering this, transforming a blurry shadow into a high-resolution scan. Yet with each improvement in resolution, new, subtler questions will undoubtedly emerge. This is the nature of cosmic exploration. Every cleared horizon reveals a further range of mountains to climb. And what lies beyond the mountains we can already see. Our story settled on a cosmic tug of war between our Laniakea Supercluster and the even more massive Shapley Supercluster. But is Shapley the final word, or is it too in motion? Could there be structures of such immense scale, so vast and diffuse that they barely register as overdense regions in our current surveys, that are pulling on Shapley itself? Some cosmologists speculate about the existence of unimaginably large gravitational influences, mass concentrations on scales of over 1 billion light-years, that could be shaping the bulk flows of entire supercluster complexes. Detecting such subtle, universe-spanning ripples is at the very edge of our observational capabilities, a whisper nearly lost in the roar of the expanding cosmos. The question pushes our understanding of the cosmic web to its limits, asking if the patterns we see are merely local texture on a fabric whose full design we have not yet perceived. Closer to home, within the borders of our own Laniakea Supercluster, smaller mysteries churn. We understand the broad flow toward the central basin, but the motion within that flow is complex. How do individual galaxy groups and smaller clusters interact as they travel this shared river? Do they jostle and merge like logs in a current or stream past one another smoothly? What are the precise gravitational eddies and minor attractors that influence galaxies on their long journey? Answering these questions requires not just a static map, but a dynamic movie of our local universe, tracking positions and velocities with ever greater precision over time. Projects like the Vera Rubin Observatory will provide exactly this, a decade-long time lapse of the sky that will let us watch the cosmic watershed in motion, revealing the finer hydrology of our immeasurable heaven. This cascade of questions is not a sign of failure, it is the signature of a living science. The story of the Great Attractor beautifully illustrates how discovery works. Each breakthrough, from finding the anomalous galactic motion to piercing the zone of avoidance to mapping the dark matter web, did not provide a final answer. Instead, each solution refined the mystery, lifting the veil to show a deeper, more intricate puzzle waiting beneath. The unknown is not a wall we hit, it is a frontier that recedes before us, inviting us further in. Our pursuit of this hidden mass has fundamentally changed our view of reality, teaching us that the universe is built from something we cannot see, and that we are all riding currents set in motion at the dawn of time. The final lesson of the Great Attractor may be this: the cosmos is far stranger and more wonderful than we ever imagined, and its greatest secrets are still waiting, hidden in plain sight. Our pursuit of this hidden mass is at its heart a deeply human story. It begins not with a grand revelation, but with a simple, nagging discrepancy. Someone somewhere looked at the numbers describing our galaxy's motion and realized they did not make sense. That initial moment of curiosity, of recognizing a flaw in the expected pattern, set everything in motion. From there, the story unfolds as a classic scientific drama, a persistent effort to see the unseen. Each time our view was blocked, we built a new window. When visible light failed, we learned to listen with radio ears and feel with infrared hands. When the sheer scale of the pull defied explanation, we conceived of invisible dark matter to account for the missing weight. And when we needed to understand our place in this new architecture, we became cartographers of motion, drawing the borders of superclusters not by where the stars are, but by how they flow. This entire epic, from anomaly to understanding, is a testament to a specific kind of human ingenuity. It is the ingenuity of stubborn curiosity, of refusing to accept that something cannot be known simply because it is hidden. The Milky Way's own starlight was our greatest obstacle, a brilliant veil drawn across the truth, yet we did not give up on the mystery behind the curtain. We developed the tools to pull the curtain aside. The journey to map the Great Attractor mirrors countless other journeys of discovery. It shows how science operates not as a sudden flash of enlightenment, but as a slow, collective turning of a lens, bringing a blurry shadow into ever sharper focus. Each generation of astronomers built upon the puzzles left by the last, using new technologies to ask deeper questions of the darkness. What started as a single anomalous velocity became a map of a continent, and that map revealed we are part of a river whose source and destination stretch across the eons. This narrative arc is our greatest takeaway. The cosmos is under no obligation to be obvious to us. Its grandest structures and most powerful forces are often concealed, either by distance, by time, or by the very nature of reality itself. Our role is to patiently, cleverly piece together the clues it leaves behind. The story of the Great Attractor is not finished, but the chapter we have written so far reaffirms a powerful idea. No matter how obscure the path, human curiosity will find a way to follow it, lighting up the hidden architecture of the universe, one stubborn question at a time. So the story comes full circle, but the view is forever changed. We began with a simple anomaly, a galaxy moving too fast, and followed that thread into the deepest cosmic shadows. What we found was not a monster, but a map. The Great Attractor is the profound gravitational heart of our home supercluster, Laniakea, a focal point where the rivers of 100,000 galaxies converge. Its immense pull, the force that steers our Milky Way at over 1 million miles per hour, comes not from the brilliant islands of stars we can photograph, but from the vast, unseen ocean of dark matter in which they float. This hidden architecture is not static. It is part of an endless hierarchy, a cascade where our attractor is itself pulled toward the even greater mass of the Shapley Supercluster, all while the accelerating expansion of dark energy stretches the canvas of space itself. To grasp this is to undergo a fundamental shift in perspective. We are not still. We are not at the center. We are participants in a slow, majestic flow that began with the first gravitational whispers in the early universe. Our planet, our sun, every atom in our bodies is caught in this current, riding a dark matter filament toward a destiny set billions of years before life arose. This knowledge transforms our place in the cosmos from one of isolation to one of profound connection. We are literally made of stardust, and that stardust is on a journey guided by the invisible skeleton of everything. The ultimate revelation of the Great Attractor is that the universe is built from a reality we cannot directly perceive, a lesson in humility and wonder. It reminds us that the most significant forces shaping our existence are often the ones we must deduce from their subtle effects on the light. So the next time you look up at the night sky, remember you are not just looking out into space, you are looking along the current of an immense, dark river flowing toward a hidden sea. Let that feeling of motion inspire you to stay curious, to keep questioning, and to always look for the hidden architecture behind the visible world.